video for October 23rd. Let's go ahead and get started with this due now here. So I want to graph the following and to describe the transformations on y equals the absolute value of x. All right, this is a unit 1 topic, but what we'll see is that vertex form of a parabola is very similar to this. Okay, so first I'm going to describe those transformations. This -1 here is going to move us to the right 1. This +3 here is going to move us up 3. And this 2 here is going to cause a vertical stretch of factor 2. I'll write that out, of factor 2. So how I graph this is I don't have to use a table. I can just memorize the one parent function, y equals the absolute value of x, which is a v-shaped graph centered at the vertex, or its vertex is centered at the origin, with a slope of 1 and -1 to both sides. All right, so I'm picturing that, and then I move it right 1 and up 3. Here's my new vertex, and then the vertical stretch of factor 2 means that now the walls are a little bit steeper. Now they have a slope of 2 and -2 off to the sides, and I can connect those up to make a V-shaped graph like that. Okay, vertex form of a parabola is going to be very similar. We just have a slightly different parent function to memorize. So our goal today is to be able to graph a quadratic using the vertex form. Why are we doing this? Each of the values in vertex form enables us to change the graph in a precise way. All right, quick question. What do we remember about quadratics? Okay, hopefully you were able to come up with a few things. Finish the sentence. A quadratic equation is... All right, this is how I would finish the sentence. A simplified equation in which the biggest exponent on a variable is a 2. All right, if the biggest exponent is a 2, we're dealing with a quadratic. Oh, you copied that down. Now, which of the following are quadratics? Just type their number. 1, 2, 3, 4, 5. Okay, let's go through them. This first one is not a quadratic. All right. In fact, what we call this type of equation is a linear equation. All right, linear is where the biggest exponent is a 1 and we don't even have to write it. This is an x to the 1 right here. This next one is a quadratic. It doesn't have to have a linear term to be a quadratic. This next one is not a quadratic. Although I see the exponent of 2, this is not simplified. 3 squared could be rewritten as a 9 and then combined with this 2. This one was also linear. The exponent has to be on a variable. The next one is a quadratic. This one does have that linear term. And then the last one, nope, the biggest exponent is a 3. The word for this one is cubic. If the biggest exponent is a 3, it's now cubic. All right, is this a quadratic equation? Well, it has to be a simplified equation, so we're not sure yet. We see this 2 here, but we're not positive if that's going to end up on this x, so we got to simplify it. All right, so these steps here, this is how we convert vertex form to standard form. We need to be able to do this. So anytime I see a squared, that means take the base and multiply it by itself 1 time. So the base of this exponent is that whole expression there, x plus 4. So I got to repeat the x plus 4 twice, keeping a set of parentheses around it. All right, now we have to do a type of distribution that's so common it gets its own acronym. It's called foiling. And FOIL stands for first outside, inside, last. But essentially, whenever I multiply two things that are in parentheses, I just have to make sure that every term in the first expression gets multiplied to every term in the second. FOIL is useful to make sure you get all four possible combinations here. But when these get bigger, I just think first to first, first to second, second to first, second to second, and so on. All right. So first to first, x times x, that's going to become an x squared. And we can draw a little arrow to show that we multiplied those. Outside, x times 4, that becomes a 4x. Inside, 4 times x, that becomes another 4x. And last, 4 times 4 becomes a 16. Keep this minus 3 at the end. And now we're just one step away. All we have to do is combine our like terms. And this will be simplified. Y equals x squared plus 8x plus 13. So is this a quadratic equation? Yes. The biggest exponent on a variable is a 2. And what we just did there is we just took vertex form and converted it to standard form. All right, when graphed, a quadratic creates a parabola. Let's all add this diagram to our notes. Parabola can have a y-intercept. Well, all parabolas have a y-intercept. Not all parabolas have x-intercepts if it hits its vertex before it crosses the x-axis. The vertex is where we turn, just like in an absolute value graph, and then you get your line of symmetry there. All right, here is the parent function y equals x squared. This is the one you have to memorize. You have to memorize all of these dots, but it's pretty simple. These are just our perfect square numbers. You know, when I'm at 0, 0 squared is 0. All right, if I go over 1, 1 squared is 1. If I go over 2, 2 squared is 4. If I go over 3, 3 squared is 9. All right, and it's the same over here, 1, 4, 9. So sometimes 1, 4, 9 is enough to memorize to get enough of the graph that it either goes off the graph or we've got its general shape. So you can just remember, basically what I'm saying is memorize your perfect squares. The perfect squares. And you can go up, you know, you don't even have to go that high. 1, 4, 9, 16, 25, 36, 49. If you need any more, you could just start actually squaring numbers in your head. But yeah, I'll just kind of write this out. Dot, dot, dot. Okay. Normally 1, 4, 9 is enough though. Okay, so on that earlier slide, I said that was vertex form. Here, let's write out vertex form with just variables. Go ahead, copy this down. When it's in this form, it's so similar to the absolute value graph. H and K is still the vertex. All we have is this 2 up here, and we don't have those absolute value brackets. All right, another way to think of H and K is horizontal shift and vertical shift. It moves the vertex, but it also moves every single other point. That same amount left and right, up and down. And then A works the exact same as with those V-shaped graphs. The parabola is skinnier if A is greater than 1. It's wider if A is between 0 and 1. It opens up if A is positive, opens down if A is negative. You can pause this and copy down all this information too if you want. And let's start practicing some off of that worksheet. Here we go. Sketch the graph of this function. First, let's write all the transformations that are happening. So this minus 4 is going to move us down 4. This negative is going to cause a vertical flip. And this plus 3 is going to move us left 3. It's always kind of opposite of what you think. On that h value, you see a plus 3, that's left 3. Okay, so let's position the new vertex. It was at 0, 0. Now it's been moved left 3 and down 4. There's my new vertex. And I'm going to label it -3, -4. But now we've got to figure out how to add in the parabola. It's been flipped upside down, so don't sketch this, but it's going to look kind of like this, right? But I want to get the precise values. So normally, as my parabola goes out, it goes up 1, 4, 9. But I'm going to multiply all of these by the a value of -1 to get that the new pattern now is -1, -4, -9. So as I go out 1, I'm now going to go down 1. So out 1, down 1, out 1, down 1. The a value is also how far you go up or down on your first move. Just like, I mean, that's exactly the same as those V-shaped graphs. All right, but now if I go out 2, I'm not going to go up 4, I'm going to go down 4. So I go back to the vertex, I go out 2, now I go down 4, 1, 2, 3, 4. And I make it symmetrical. And then you can connect these up, try to do like a nice smooth curve. And there we go. Easy as that. 1, 4, 9 became -1, -4, -9. Always remember to keep going back to the vertex as you add in those points. Let's try another one. This one has been moved up 2. It's been moved left 4. And it's been vertically stretched. So all right, let's position that vertex first. It was at the origin, now it's been moved left 4 and up 2. Here's my new vertex at -4, 2. And now the pattern 1, 4, 9, everything's going to get multiplied by 2. So as I go out from my vertex, I'm going to go up 2, 8, 18. All right, so this is all times 2, which is the a value. All right, so back to the vertex. If I go out 1, now I'm going to go up 2, make it symmetrical. Back to the vertex. If I go out 2, now I'm going to go up 8. So bring me all the way up here, make it symmetrical, and I'm off the graph. All right. And try to make your parabola look good. Little arrows at the end to show that it goes on forever. All right. Number 7 says, let's go the other direction. Let's write this into vertex form. So first let's label that vertex is at -4, 2. That gives me my h and my k value. So I can already write this part, y equals, leave a little blank for a, x minus h, which would become a +4, because the minus and negative becomes a plus, squared plus 2. Now I just have to figure out what the a value is. And the trick is just go over 1 and then count up to the vertex. I only have to go up 1. So my a value is 1. I don't have to write it, but there's a little invisible 1 right there. Okay, here's another one. Vertex this time is at -5, 0. So I've got y equals x plus 5 squared, and I don't have a k value to add on at the end. But now if I go over 1, it looks like I go up maybe a quarter. If I go up over 2, then I definitely go up 1. I was supposed to go up 4, but now I'm only going up 1, so that does confirm for me that this is a 1/4. It's been squished by 1/4. And then this one would be 2.5 or 2.25 up. This one would be exactly 4 up. But if I want to do it a different way, I could just kind of pick a point that it definitely goes through, like -1, 4, plug that in for x and y and solve. So this is a different way to get the 1/4. Now I've got 4 equals a times -1 plus 5 squared. 4 equals a times 4 squared. 4 equals 16a divided by 16 divided by 16. Simplify the fraction. That's another way to get that a equals 1/4. All right, but I was able to kind of just reason through it that we were supposed to go up 4, we only went up 1, so it had to have been multiplied by 1/4. All right, describe all of the transformations. We've been doing that all along. So we've got a vertical flip. We're being moved. Nope, not right. I almost got tricked there. Left 2 and down 2 or down 3. And I think you can do this one. All right, that's that for this presentation. I'll put in a couple more practices of that foiling to turn vertex form into standard form. Standard form, when you write out with just variables, is this, by the way: y equals ax squared plus bx plus c. But yeah, it's just what you get when you fully simplify something and put it in order of descending exponents. All right, we'll call that good for this. Have a good rest of your day.